Hi, we are back, and then this is a clip number 4, and it's a final clip to wrap up about the application of differential equation to some basic engineering system. Okay. From last clip, okay, we extend how the use of differential equation to model a kind of higher order system. Higher order is mean that the order is of differential equation is greater than 2. Okay. From last one we have used this the example of electrical network. Okay. Now we're going to move on to another higher order system, but this one is based on this figure. Okay, the two mass, okay, connected with the classical mechanical element, okay, the spring, and with constant in case of 1 in case of 2, and these are two damper or two first order system, okay, element of C sub 1 and C sub 2, and then certainly the second order element of these two masses of M sub 1 and M sub 2. Okay, from this figure, okay, this for all of this mechanical element, okay, trying to resist the force of Ft, function of T, okay, the dynamic force, okay, and that's gonna cause the displacement of both mass, okay, both masses, okay, and then all of this mechanical element try to resist this force, okay, and it's the same as we use Kirchhoff voltage and Kirchhoff current law, okay, to analyze the electrical circuit. Okay, this one we can apply the concept of Newton's law. Okay, and the resulting governing equation can be written in the following form of the matrix system, equation system. Okay, we're going to call this as a matrix of A, and you have two response vector that you are looking to find. Okay, the function of x sub 1 t and x sub 2 as a function of t. Okay, and again we're using a d operator to represent d by dt. Okay, where is this governing equation coming from? Okay, it's coming from, I'm not gonna review much because this one is based on what you study in the basic mechanics, okay, especially in the part of dynamics in mechanical dynamics. Okay, let's look at the we in engineering analysis we call this a free body diagram. Okay, that we trying to look at the mass m sub 1 here. Okay, the mass m sub 1 have the two spring connected and two of the damper, okay, to connected also. Okay, this cause the movement of x sub 1 here. Okay, it's therefore this is concerned with this one. Okay, the element in the matrix A related, you can see based on metric multiplication, this element of m1 d square, which is second order of differentiation, okay, plus summation of c1 plus c2 times first order and plus k1 and k2 of first order. You can see that this is all the mechanical element that related to this. When you look at this mass m sub 1, okay, m sub 1 is connected by these two spring and connecting by these two damper, and it with the mass m sub 1, okay, this caused the displacement of x sub 1 reflecting, try to resist the force of ft, but if function of t did not apply directly to m sub 1, but it receive the effect of forces from m sub 2. Okay, and all of this element also trying to resist, okay, the movement, okay. So in the first part here, okay, if you understand free body diagram, okay, so this is all the element m sub 1, and you say d square, when you apply to x sub 1, it become the acceleration of x of acceleration of mass number 1, okay, and c1 plus c2 dx, when you apply to this, it become dx sub 1 function of t by dt, okay, and that's the response of combining response based on both of these damper element, okay, that connected with m1, okay, this are all for x sub 1, but based on the matrix multiplication, this element after the, let's look at this is the a sub 1 1 element in the matrix of A, which means that in the row 1 number 1 in matrix of A multiply to x sub 1 t, okay, but you have to minus c2d minus k2 time to x sub 2t also. What does this happen? This happen because the element of k2 and c2 here also connected, not only connected to m1, but they are connected to m2 also, based on the free body diagram, okay. Therefore, the resulting movement, okay, here, okay, have to be k1 plus k2 x sub 1, but actually is have to minus k2 x2 also, because it become the relative displacement. Relative displacement of the system is become x sub 1 minus x sub 2. When you look at this from this side of free body diagram of m sub 1, okay. Therefore, you need to minus, okay, c2d minus k2, which is the element of connected element between m1 and m2. But when you look at the m1 side, this one become the negative side, okay. And that's again, when you look at mass number 2, okay, mass number 2, only the element that connected m2 is only k2, c2 and m2 themselves, okay, and therefore this is only, okay, m2, the acceleration of x sub 2 plus c2, the first order of x sub 2, and k2 x sub 2. But again, okay, when you look from this side, okay, these two elements k2, k sub 2 and c2 also connected to m1, okay. Therefore, you need to subtract, okay, subtract the x sub 1 here, okay, just like what you did when you consider at m sub 1 on the first equation. Look at it, the same as minus c2d minus k2, but this one you multiply by x sub 1, okay. And in other words, you can look at that the relative displacement, okay, when considering k1 and k2 here, when you look at m1 is x sub 1 minus x sub 2, okay, and also the relative displacements for m2, okay, when you look at free body diagram of m2 is x sub 2 by minus x sub 1, okay. So that's why resulting this equation, and you can rewrite in a metric form as shown here, okay. And certainly for m2 is connected with the direct applied force function f as a function of t here, okay, and certainly this one have to be the input force, okay, here, input force based on the balancing of the Newton's law, okay. When you apply this is all the resisting force, okay, based on x1 and x2, okay. This one is from x1 and x2. When you, this second equation consider free body diagram at m2. The first equation considering the free body analysis of free body diagram of m1, okay. Hope this is not just trying to recall your old memory of the basic static and dynamic course in engineering, fundamental of engineering analysis, okay. So this one can be written in the matrix form, It looks like a second order system when you consider it. Okay, because it consists in the metric consists of d square, which is the second order differentiation. Okay, but when you look at this, okay, you know that this is a system of equation consists of two variables. But to solve a differential equation, you need to make it to rely on just only one. You need to have only one range, okay, with a single domain of t. Okay, that's why we need to rewrite this again by trying to derive x of 1t and x of 2t to have two different independent two independent differential equations to solve. And the way to do it is that you're going to solve this metric system symbolically, okay, based on this symbolic of mathematics. And certainly, since it's only 2x2 equation, you can apply the direct Cramer's rule here, okay, which certainly you, just like a previous example, okay, you start by finding the determinants of A first, okay, the determinant are going to be like a delta 0, okay. Certainly, this one, based on this element, you use the diagonal element, multiply to each other, okay, and then minus, okay. Since it's all minus times minus become plus, so the remaining minus still becomes C2D plus K, okay. Actually, it's minus C2D, minus all the bracket C2 times D minus K2 and the close bracket, okay. And since they are minus within these two elements, they multiply each other, plus minus become plus, but based on the determinants formula, it's still minus, still whole, and this one becomes C2D plus K2 square, K2 square. So just once you multiply these two, you get the fourth order system here, okay. I'm not gonna explain much about this. It's a very simple algebra, okay. You can multiply this one m1 times m2 d to the 4, okay. For d to the 3, you need this to multiply to this, and this multiply to this, okay. D square times d in the second term again, and then the d square second term multiply to the d term in the first equation here, okay. So you get this d square d2 and all of this, okay, times these, and then zero order here, and then you also need to expand this term of a square and rearrange the term. Rearrange the term. This means that like this one minus c square times d square, okay. You need to use this to put it in the term d square here, okay, and also minus 2 times c sub 2 k sub times k sub 2d. You need to move this to kind of balancing. Some term may be cancelled out, okay, when you put this in here. And minus k square, so minus k square is easy, you see that. Plus k square here, k square times k sub 1 plus k sub 2. This one k square minus k square cancel each other, okay. So the only remaining term will be k sub 1 times k sub 2 here, okay. So that's the evaluation of delta 0. I already did this for you, okay. To simplify it, I'm going to use the coefficient term that multiply d to the 4 here, okay, the fourth order term as a small a, and the coefficient multiplied to the third order derivative here is b, okay, and this term for the second order, okay, it will be small c, and then small d for the first order term, and then small e for the zero order term, okay. And again, when you apply the Cramer's rule, you know that x of 1t will be equal to delta 0, and certainly you can find delta 1 by finding the determinants. If you want to find x of 1 as a function of t, you just put the right hand side vector here, okay, column vector here, to replace the first column and find the determinants. For x of 2 as a function of t, you put the right hand side function, replace it on the second column here in the matrix A, and then find the remaining find the determinants of the resulting matrix. That's what we did here, okay. We put here in replacing the first column, okay, and find the determinants. And delta 2 is this one. You put 0 and ft, which is the right hand side function, to the second column, and then find the determinants here. Okay, and this is a resulting evaluation of symbolically of the determinants function here. Okay, once you get delta 1 and delta 2, you use delta 1, okay, divided by delta 0, you get x of 1t. Okay, x of 1 is function of t, and you use the delta 2 divided by delta 1 or delta 0, okay, delta 0, okay, as that's the result x of 2t. Okay, and then you can move by rearrange the term, okay, and get this two following fourth order differential equation that is independent of each other. Okay, x of 1 and x of 2 already separate, okay, not independent, not dependent, just like the matrix equation over here. Okay, so as you know that since delta 1 divided by delta 0 equal to x1 as a function of t, you know that delta you move delta 0 to the left hand side, you get delta 0 x1t equal to delta 1. So this one you just replace d by dt and d squared by d second order and third order and fourth order. This is the right hand side. This becomes the right hand side function. Okay, and delta 0, okay, times, okay, delta 0 times x1t become the left hand side, and the second equation become delta 0 times x2t become the left hand side. Okay, that's resulting this one. This is the left hand side, this is the right hand, and this is the right hand side. So now you are having two fourth order differential equation here to solve. Okay, so we're now gonna continue to use the similar analysis that we did for starting. You remember that we start from first order example, second order example, and the last clip is a third order example. Now it's a fourth order example. Okay, let's consider fourth order example. Therefore, but you have to remember that in this case you have two function you want to find. You want to find x of 1 as a function of t and x of 2 as a function of t. Certainly it's going to consist of complementary solution here. I put it in here in this notation, x of 1 c as a function of t plus x of 1 p as a function of t. C mean complementary solution, p is a particular solution. x2 and x2c as a function of t plus x2p as a function of t. Since there are two, so you need each of them need 4 both initial or boundary condition here. Okay, in this case you want initial condition, okay, or x1. For boundary condition you can have x1 and then the first order boundary condition is sufficient to find all the constant in the complementary solution. Okay, you can see that to finish solving this problem completely is using your knowledge of ordinary differential equation solving procedure is quite tedious task also. Okay, you can look at this example. Okay, to find x of 1c and x of 2ct. Okay, first, okay, it's easy to see that both equations have the same characteristic equation. Okay, or auxiliary equation is as to the 4 plus bs to the 3 plus cs to the 2 plus d times s plus e equal to 0. Because all this d by dt you just replace by s and power by the order of the d terms. Okay, so this one. So now you end up having what we call the quartic equation. Okay, you need to solve the root of the quartic equation. Okay, and we're gonna search, okay, from the Google also, that once you have, just like last time, we have quartic equation. Okay, this one. When you look at the quartic equation, do we have a general form? This one, you just replace x by s. Okay, but from out here, okay. Actually, this is a very big statement. The quartic is the highest order polynomial equation that can be solved by radical in the general case. Okay, which means that you remember in the second order we have well-known formula to solve the root of the quadratic equation, but the formula getting a little bit tedious or a little bit complicated when you move to the third order. And fourth order, this one, theoretically, mathematicians have proven that if the root of the polynomial equation start with the fifth order, okay, polynomial function, or in other words, we can call quintic equation. When you reach a quintic or sixtic, the order is 6, you cannot write any general formula. Okay, there are some mathematicians prove it. Okay, many years ago, and you might know, you might have heard about Abel prize, the highest prize of for mathematician. Okay, Abel was a Norwegian mathematician, and he was the one. Okay, along with his colleague, if I'm not mistaken, that have proven that for the polynomial function, okay, with order greater than 4, okay, start from 5, 6, 7, okay, you cannot be solved by radicals in general case. Okay, so the bus stop here, okay, at the quartic equation. That's why we're gonna propose this. This is going to be the last example. Okay, and one way is that from the fifth order, very hard to find a general form. Certainly, the Wikipedia did a great job. Okay, but they, if you want to find a general form, okay, this one it will be good for you. Ferrari's method, the summary. Okay, quartic equation. The capital A is the same as us. Okay, you need to find alpha, beta, and gamma according to this formula. Okay, and you want to check if beta is 0. Okay, then x is equal to here. Okay, equal to here. You see minus, plus, minus, and plus, minus here. Okay, you see that? Okay, plus and minus here. Plus and minus here is mean that you have 4 root, right? X have 4 possible. One is plus, minus, plus, and minus. Okay, this one for beta is equal to 0 only. Okay, otherwise, okay, if beta is not 0, you can use computed P, Q, and R, and then you end up having this formula. Okay, and you can see that it's a very much more complicated for the fourth order here. And if you really like mathematics, you might go and look for more explanation in the this one also derivation. Okay, second perfect square. I'm not going to go to this because I just show it for you that to analyze this. Okay, you can look at, but you can have to be very seriously look at the step by step. Okay, to find the way to derive the general formula here. Okay, but if you want just one formula, you just summarize it here. Okay, that's pretty complicated one. Okay, they also have similar way that many people try to find the way. Okay, this is another way. Okay, to get all the root also, many ways that you can find. Okay, but we're not gonna pay much attention to this anymore. I just want to show you that, okay, to derive a general formula, the bus stop here. You can't go any further than to the fifth order. Okay, so it means that, okay, based on this information, okay, we can find the root here, derive, have a general formula to find S, all 4 root here. Okay, otherwise, what about if you go to the fifth order, sixth order, when you don't have any formula? So you need to use what we call the numerical method. Okay, you just search the Google and numerical method for polynomial function. Okay, and also I want to show you something that in Google there are some what we call the finding roots of polynomial. Okay, and you can see that just put online. Okay, you can see that this is a very directly for you that you can have polynomial root calculator online here. Okay, and you can like here, okay, you can enter the formula here and then they will find the root for you online. Okay, so you might try it out when you and it's for free. Okay, but I don't know how long can they go, how many further, how many, but this one only. Okay, the calculator compute exact solution for quadratic, cubic and quartic equation. Okay, quartic equation, but I'm not sure if you have a higher order, okay, like order 5, order 6. Yeah, they should be able to find like this one, find root here. Okay, you have 5th order here. Okay, you might try it out, but there are so many way, even Wolfram Alpha also. Okay, have some thing that you can do it online. Okay, this another way that you dealing with, you need to go any further higher order. Okay, you don't need an exact formula, but you know that the exact formula mathematically, if you know it in general case, just like when you analyze the second order, you can separate the condition that, okay, if this happen, in this case gonna happen, so it's gonna imply that you end up having all the real root or some part of real root, some part of complex conjugate. Okay, so now we're going to just assume that, okay, suppose we were to solve this and obtain 4 roots, okay, of s, representing by s of 1, s of 2, s of 3, and s of 4. Okay, you can see that the condition become huge here. There are 9 possible cases. Remember for the third order, how many cases do we have? Remember that? Okay, you might go back and look at the third order system here. Okay, this is the third order. We only have 4 cases. Okay, from page 22. Okay, but now we move on to here. Okay, page 32. When you have quartic equation, okay, you end up having 9 possible cases of root. Okay, we're going to take a look at and each type of root, you know that each type of combination of the type of roots that can happen, leading to different type of complementary solution. Okay, you can see that the first one, easiest one, is that when all are real number, all root are real number and are non-equal. Okay, they're not equal to each other, so you end up the first term corresponding to the first root s of 1 is c sub 1 times e to the s sub 1 times t. Okay, the second term, okay, additive form, similar form with new constant c sub 2 e to the s sub 2 times t, and so on until the fourth root. Okay, and that's normally you know this. So x sub 1 complementary solution t is this formula. The second one is, okay, you know that, okay, if there's a pair that equal all real roots also, but there's one pair equal, but not equal to the other 2. So you end up, okay, you can see that c sub 1 and c sub 2 here. C sub 2 need to times t, e, and then the same exponent of s sub 0 times t, which is equal, s sub 0 is the same number for s sub 1 and s sub 2. Okay, but in s sub 2, instead of when you have s0 equal to each other, if you can see that if they are same, you can combine these 2 terms. But once you times t here, you cannot combine. Okay, so t here, that when you have same root number for one pair, our 4. Okay, so the other two just follow the same as the first one. The third one is that you have three equal root and not one non-equal. So this one is c sub 1 e, and the second term becomes c sub 3 t square, okay, e to the s0 t, you know. Okay, this is one extension analysis from the case of third order, and the fourth order is just the same because it's a distinct root. And the fourth case is that all 4 are equal to s sub 0. So this one become you can see that become a exponent with combining with polynomial order t, order 3 of a domain t. Okay, c sub 1 e to the s0 t plus c sub 2 times t e to the s sub 0 times t plus c sub 3 times t square, okay, e to the s0 times t, okay, plus c sub 4 t, the cubic of 3 times e to the s sub 0 times t. Okay, that's so the first 4 cases, okay, all real roots, okay, there's no complex conjugate. The fifth case is still, okay, that you might have a pair equal to each other, but it's not equal to the other two, and the other two also another pair that equal. This one s1 equal to s sub 2 equal to s1 0, okay, and it's not equal to s sub 3, which is equal to s sub 4, which is equal to s sub 2 0. Okay, so I just hope that you can understand. It's the same s, but this one have two index. Okay, this one have only one index. So in this case, the formula just apply this similar formula to the. So the first two you have only c sub 1, c sub 2, s e to the s sub 1 0 times t, s sub 1 0 times t, and c sub 2 need to multiply by t. Ct and t4 is the same for s sub 2 0 here. Okay, so this is the characteristic equation for it's a complementary solution, okay, in the fifth case. So in the sixth case is become that, okay, you start having complex conjugate. Suppose s3 and s4, s sub 3 is a complex conjugate written in the form of p plus minus j is the square root minus 1, j times q. Okay, and while s1 and s2 is non-equal and also real number, so now you have complex conjugate. You need to add the general form of complementary solution of complex conjugate here for the constant c sub 3 and c sub 4 here. It's well known, right? E to the real part times t, okay, and you have c constant time cos of the imaginary part times t plus c sub 4 sine the imaginary part q times t. Okay, this is to handle the s3 and s sub 3 and s sub 4 as a complex conjugate. But the first two terms, okay, the same because it's a distinct root. The seventh case is also really easy to guess, okay, when the other two root is real root and equal. Okay, so you need to use the equal the repeated root formula, okay, for complementary solution here. And this one you need to have a formula for the complex conjugate. CC is an abbreviation of complex conjugate. Okay. In the eighth case, okay, there's two complex conjugate. S1 and S2 is a p sub 1 plus or minus j times q sub 1. And it's not equal to s sub 3 and s sub 4, which is another complex conjugate. P sub 2 plus minus j times q sub 2. And p sub 1 not equal to p sub 2, q sub 1 not equal to q sub 2. So this one you need to apply complex conjugate on both of these terms. Okay? And the fourth one is the last one is that you have two complex conjugate and they are all equal. Okay? Like two complex conjugate repeated, okay? Two repeated root of complex conjugate of p sub 0 plus minus j times q 0. So it's use the extension of the x1ct as a function of t, the complementary solution in the 8th case. But for the 9th case, okay, you just multiply t here to the exponent of the second term because your exponent is the same, p sub 0 t, and in the 8th case p sub 1 p sub 2 not equal. When it's the second case, since p sub 0 is p sub 1 equal to p sub 2 is p sub 0, okay, so So the second term you need to multiply t here. Okay, let's guess about it that if you start having a fifth order, how many cases gonna happen? It's gonna increase a lot. So and in each case you know that for each x1 ct here or complementary ct here, there are 4 constants you need to find: c sub 1, c sub 2, c sub 3, and c sub 4. Okay, you need to find in each case 9 cases here. Okay, but before that you need to find x1 pt, okay, particular solution of x of 1 as a function of t, and particular solution of x2 as a function of t. Okay, and also you have 9 cases of complementary solution. You can see that the complexity start to really increase just you move from one order to one order. A similar way that when you look at the root of polynomial also, the easiest one when you look at is when you have a quadratic equation, right? When quadratic moving to cubic, last time in the last clip, you can search on the Wikipedia, you saw that the formula start to not very friendly. And today we just search for you for the general formula for the Quartic. The formula is just as much as complicated or even more than the third order. Actually the third order and fourth order are not much different in terms of complexity in the formula, but still much more complicated as comparing to the well-known quadratic. That's resulting the same thing when you solve the higher order differential equation. When you move up from the second order to the third order, system become more complex. Okay, the equation become more complex. And now from third order to fourth order, even more complex. Okay, and you can guess that when you go to fifth order, sixth order, very, very difficult one. But actually I can tell you in advance that for engineering point of view, okay, you can see that this one is only we end up having a fourth order because we try to not solving this problem in the metric form. We try to change it to a general form of order differential equation which have only one domain and one range, okay, or one response, whatever you say. But actually the original system is not the fourth order, it's just a second order system connected to each other. Okay, the same as the electrical circuit system, okay, that I analyzed from you last time, this one, if you might remember. Okay, this one. Okay, you know that if the system of electrical circuit have only resistor, it will be zero order. Okay, but once you add an L or inductance or capacitor, the order start to increase. But like in this one, you have 2 inductance and 1 capacitor. That's why the resulting system becomes the third order. Okay, but actually when you we will show you later that because this one we just derive it by using the Ohm's law themselves, so the resulting becomes the third order system. But there's some way, because each element is not the higher order themselves, it's only the first order, and this one is even -1 order. Okay, the capacity, since the resulting is an integration instead of is 1 over d. Okay, so when each element is only a single order, okay, there's some way that you can reformulate the problem here, okay, or even this system here, okay, to a system of in the metric form in the equation. And the equation, the element in the equation will be only either first order or second order, as you look at here. In mechanics, the reason that you still have second order because second law of Newton. But in electrical system, it's mostly the first order, unless you combine several differentiation, the electrical component that have a differentiation characteristic, okay, combined in one term, they're going to be a higher order. Okay, if they have multiple items like that and you combine into just one item. Okay, but if you only consider the single item one at a time, when you reformulate the problem as a metric form, it will consist only either first order or second order, and that can help you there's some other way to analyze all of this, and then in a much simple way than trying to do what we are doing here. Okay, so this one I just want to show you that how the higher order differential equation system can happen. And you can see now when we reach the fourth order, the analyze start to go very huge, require a lot of derivation in many conditions, okay, to get the general solution form. Okay, so now we have 5 cases of complementary solution, and we have 2 response, okay, of x sub 1 and x sub 2. Okay, so the same way x sub 2 ct here, okay, the nice way is that both of these complementary solution 9 case can be applied to both x sub 1c and x sub 2c because they have the same left hand side form. Okay, that's resulting that they're going to end up having the same root. Okay, but each of them you need to have 9 conditions here for x1 ct, and you have to understand that toward the end that the constant c sub 1 to c sub 4 for x sub 1c and x sub 2t will be different because the x1 pt, x sub 1 pt and x sub 2 pt is different. Okay, why different? Because the right hand side is different. Okay, as you might remember that the particular solution highly rely on the right hand side function. Okay, so we're gonna do some example for you. Okay, after this. Okay, now we suppose that last example we're using the what we call the summation of sinusoidal signal in different frequency. Okay, now we are back to the general polynomial order R here. Suppose the force function can be represented as the polynomial function of order R. Okay, certainly you need to find the first order here. Why? Because one of the right hand side here, okay, you need to find this one, and this one you even have to find the second order if you want to analyze for x sub 2t. Okay, so we're going to show you how to solve the first equation first for x sub 1t. Okay, this one. Okay, so you need, this is the right hand side for the equation, that fourth order equation concerning x sub 1 as function of t. So this one c2, okay, plus k2. Okay, what does c sub 2 mean? Okay, I did make a mistake here that the notation just kind of become collapsed to each other that you might confuse about it because I'm using c sub 2 here. Please understand that c sub 2 here for complementary solution is different from here, c sub 2 here. This c sub 2 is a constant parameter for, I should do something else like c1 star, c sub 2 star. This c sub 1 and c sub 2 is a damping coefficient. Okay, it's a damping coefficient for each damper. Okay, so make sure that you differentiate that. Okay, this c sub 2 here is a c sub 2 from damper parameter, is a parameter value of a damper number 2. Okay, so this c sub 2 here, okay, and a1, a0, okay, just put the replacement here. This c sub 2t multiply here, and then plus here, and you start to combine the term. The term that multiply is a 0 order times t to the 0 is constant term. There's the combine the term that times t square times t to the third and up to t to the r. Okay, this is resulting of combining the term using a c sub 2, which is again I would like that it's not this c sub 2. Let's just say that this is a small c sub 2, not the capital. This one is a capital C sub 2. Okay, and this one you have to find it later, this constant, this whole constant. But this one we are looking for to find the particular solution, and this one we just analyze for x sub 1t. Okay, and certainly when you end up this right hand side, arrange it in this form. Okay, I'm gonna try to simplify this one by rearrange by defining this term as b sub 0, the constant term, the term that time the times the domain t is become b sub 1. The term that times the domain t square is b sub 2, you see, b sub t, b sub 4, up to, b sub r. Okay, and in general form it can be written here based on this observation. Okay, again c sub 2 here is the damper coefficient, okay, not the constant, the second constant in the complementary solution. Okay, okay, so from here, okay, we now here, this is the general one, a, small a, b, c, d, e, okay, a, x, b, x, c, d, e. Okay, this is the left hand side and this is the right hand side. Okay, certainly you know that the right hand side become the polynomial order R when you rearrange this term in general form. Okay, so this is in order R. So the concept of this one, okay, so this one you should know that based on the concept of defining the particular solution, the particular, since the right hand side function is in the polynomial order R, the left hand, and you know that you have here, there exists the first order term here, okay, x1 here, okay, and this one I forgot, is a mistake here. It should not be e. There should be like if you consider here, it should be e times x sub 1 t. Okay, d. Okay, and this is d. Okay, so this is should have e times x sub t. Okay, and this one should be x sub x, the first order. Okay, there's a mistake here. This one, the parameter d times the first order of xt plus e, the zero order xt. Okay, so the left hand side here should follow this one. Okay, so it should follow the equation here. Okay, it should be the right one. Okay, and this is the right hand side. So when you get that, okay, you know that since there exists a zero order, therefore the xipt, okay, can be written in the same format, but just a different, you need to find the relationship. Since b sub 0, b sub 1, b sub 2 up to b sub r, you can find it, right? You can find it here by using this direct substitution. Okay, and but you are looking for to find g sub 0, g sub 1, g sub 2 up to g sub r by comparing the coefficient between the left hand side and the right hand side. Okay, so now when you get here, okay, you get x1p, the first order, okay, the particular solution, the first order. Okay, use a similar way we did before. This is the first order, and this is the second order. Okay, the highest order start reducing the first order from r to r minus 1. Second order become r minus 2. Third order become r minus 3. Okay, and fourth order it's just become r minus 4. Okay, and then you can see that the constant multiplied to each coefficient start to have some factorial formula form. Okay, and just you can see the trend that going along. Okay, this one just 1, 2, 3, 4 up to r. This one 1 times 2, and this one 2 times 3, 3 times 4. This r times r minus 1. This one 1, 2, they become 2 times 3. This one 2 times 3 become 2 times 3 times 4. 3 times 4, this one become 3 times 4 times 5. Okay, up to r times r minus 1 times r minus 2, and with the order reduced by 1, the highest order. And the fourth order become this 2, 3, okay, become, and G3 become G4 because G3 become constant, no t multiply. So when you find the derivative, this term vanishes, but this one become t, 3 become 1 once you find the derivative. Okay, so this is just go along and try to look at the formula. But again, the first line here, the left hand side, maybe the line is too short. I was too early. This is a mistake. Okay, d here should multiply by first order of x, t, and it should be x sub 1, x sub 1 t. This one x sub 1 of first order, and time e x sub 1 as a function of t. Okay, so the left hand side again. Okay, let me remind you that the correct one is here. Okay, just make a mistake for writing it down here. Okay, next step, comparing coefficients. Okay, so quite some time that b sub 0, okay, this is the right hand side in terms of zero order. This is the first order of domain T, time T, and second order, up to R order on the right. For each b sub 0 can be comparing one by one with this one. But with this one, you have to know that x1 pt is multiplied by e. Okay, this one is a zero order multiplied by e. First order multiplied by d. Second order multiplied by c. Third order multiplied by b. And fourth order multiplied by a. Okay, with this concept, okay, how you can compare it. B0, okay, will be equal to, you can see that E is the first order, D second order, C third order, B fourth order, and G and this one A times in the fourth order. Let's look at it again. Here. First order, second order, third order, fourth order, fifth order. This is the term, the constant term. There's no multiplication with any t term. Okay, so this one, okay, multiplied by E, okay, D, C, B, and A, all small. This one, A, B, C, D, E, compared to B0. And then we compare the same with the term and then multiplied by T, okay, G1, the first zero order multiplied by E, 2G2 multiplied by D, and 3 times 2G3 multiplied by C, and this one 4 times 3 times 2G4 multiplied by B, and 5 times 4 times 3 times 2 G sub 5 multiplied by A, and that's resulting to this one, okay, equal to B1, B2, B3, B4. As you know that when you compare the left hand side and the right hand side, the left hand side, the right hand side go up along to the order B. But you can see that for the fourth order, it's going to stop at R minus 4. The third order stop at R minus 3. The second order stop at R minus 2. So the term start to vanish here, okay, when only to BR minus 4. Because this term keep continue until BR minus 4. Because when you compare to BR minus 4, it's only the last one that the fourth order still exists on the left hand side, okay. So when you go to B minus 3, the fourth order no more. You go for the R minus 2, the second order no more. The first order no more. And now only, and you end up with the last one is BR here. BR here, you can see that the first order, second order, third order, fourth order are all vanished because they don't have anything multiplied to T to the R. Only the zero order here. And you know that the zero order multiplied by E. So end up the last equation is that E times G sub R here. E times G sub R here multiplied G sub R equal to B sub R times G sub R. So this one have to be equal. With this system of equation, okay, you can compute all the relationship between B sub 0 to B sub R, defining G up to G sub 0 here. First, by back substitution. First, you saw the last equation. You know that G sub R is equal to B sub R divided by E, and then you substitute G sub R over here. The next to last equation, you end up be able to find G sub R minus 1. And once you know G sub R minus 1, you substitute it here. G sub R minus 1. You end up having G sub R by minus 2. The same, you have this G sub R minus 2, G sub R minus 1, and G sub R. Put it in this equation. 1, 2, 3, G sub R minus 2. You end up be able to derive G sub R minus 3. So this is just an initial substitution here. But once you know G sub R minus 1, G sub R minus 2, G sub R minus 3, you can substitute here. And then you get G sub R minus 4. And the same thing now, when you know G sub R minus 4, okay, you can continue substitute back, end up to find G sub 0. Okay, and in general, I'm not going to go through with this. I already did this for you. Okay, but you have to go and take and consider that this is a general form that G sub R minus 1, G sub R minus 2, G sub R minus 3. After G sub R minus 3, G sub J, and when start R minus 4, R minus 5, R minus 6 up to 3 to 1, it's all the same formula. Why the same formula? Okay, g sub r plus 1, g sub r plus 2 over here, because you can see that when you reach here, okay, g sub r minus 4, okay, once you know g sub r minus 1, minus 3, okay, you can substitute all of this, okay, and move it, change to the right hand side and divide it by e. You end up be able to find all the g value here, okay. This one b sub j, this g sub r plus 1, this one should be j plus 1, not r plus 1, okay. This is g sub j plus 1, g sub j plus 2, g sub j plus 3, g sub j plus 4, okay. Keep, and this one you keep replacing from j equal r minus 4, r minus 5 up to reducing down to 3, 2, 1, and 0 also, I forgot 0 here, okay. Actually this one can substitute and move you back to the original g sub 0, okay. So there's something you need to change here. This one change r here, subscript here to g sub j, j plus 1, and j here r minus 4, r minus 3, r minus 6 up to 3, 2, 1 and 0, okay, because you can find it here also, g sub 0 here in the first equation, okay. So that's you already find what we call the x1 particular solution as a function of t, because you can find now all the coefficient elements g sub 0 to g sub r to the system parameter by using this formula, okay. And then once you know particular solution, okay, as you know that particular solution for x sub 1 and x sub 2 is different because the right hand side is different. For x sub 2t you need to have another derivation, okay, to find x sub 2t here, okay. And then, okay, you move on to find c sub 1, c sub 2, c sub 3, c sub 4 for x sub 1 c of complementary solution here, okay. Supposing we considering, I just use the case number 8, I think, that you have two complex conjugate which unequal, two non-equal complex conjugate, okay, S1, S2 here, and you know that XCT general formula can be written here, and you know that X1PT, okay, is a polynomial order R with constant g sub 0 to g sub r, and g sub 0 to g sub r can be solved by using this back substitution formula. And x sub 1t is x sub 1ct, okay, complementary solution plus particular solution. And now you have 4 cases, okay, 4 initial condition. You can see that you can also analyze it. Is either the problem is the initial value problem or boundary value problem. You can see that plenty a huge amount of work to complete all the analysis of the results here. Okay, so the first condition is x sub 1 at time 0. Okay, you know this x1t is this term, the complementary solution plus particular solution. You know that when t is equal to 0, when t is equal to 0, the sign term that becomes 0. So we have c sub 1 plus c sub t plus g sub 0 equal to 0. Okay, that's the first equation. The second equation is this one is the first derivative evaluated at t is equal to 0 is 0. So you need to find the derivative of this term of complementary solution in this form, and certainly more difficult because you have multiplication function of e to the p sub 1 t, okay, times c sub 1 times cos of q sub 1 t. You have the differentiation of a multiply function, okay. So if you might remember, the derivative of u times v by dx is du, okay, u dv, okay, plus v du, okay. This one is what we did here, okay. This one is the first term is u, the second term is the term in bracket is v, and you have two terms. The first term here you separate, in two terms. This is u dv plus v, okay, v this one, du here, okay, the same as here, okay. And once you get second derivative, okay, you end up, okay, in here you substitute at t is equal to 0. Once t is equal to 0, okay, you can see that the sine term become vanished. Only the cos term remain. And also when t is equal to 0, you have to consider this one in the first order term also. In the first order term, you end up having only g sub 1 here, okay, when t, because this term is already vanished with the first derivative, but g sub 1 become constant after you find the first derivative. Okay, so you have g sub 1 here, you have p sub 1, q sub 1, b sub 2, q sub 2, q sub 2, okay, equal to 0. That's the second equation. And then the third equation, you find another the second I rewrite it again over here, okay. I try to arrange the term here, okay, try to arrange the term that cos term and sine term combine together, rewrite it like this, cos and sine, okay. So make it better to find another second derivative, again using u dv plus v du, okay, in both terms, okay. And the term keep expanding here, okay, because the term is keep longer, okay. You have to evaluate themselves, but I just did it outside and simplify the term to this form. When you multiply this, when you substitute at t is equal to 0, you end up having this type of equation, okay. The constant term become 2 times g2 because once you find the second derivative of x, a particular solution, with these two terms vanish, this one become 2 times g2, right, 2 times g2 when you find the second derivative, okay. Equal to, that's the third equation. You need one more. This the third, you rearrange the term again, okay, and the term becomes so complex, okay, start to get complex because this one c sub 1, c sub 2, you have 4 term here. So to simplify it, you have the term that multiply to cos and multiply to sine and cos q1 sine q1 cos q1 and cos q2 sine q2, okay. So I'm gonna simplify this to become capital A, capital B, capital C, and capital D, okay. You can see that the capital A is at beyond e to the p sub 1 t, all this term cos q and cos q sub 1 t, all the value in this bracket become the A, and then this one, all the value in this bracket become B, all the value in this bracket become C, and all the value in this bracket become capital D, okay. When you get this, okay, you end up having to you be able to you know that this all the constant you have, since PQ is not really all it's independent to the domain T, so you end up can simplify the derivative here, and you end up having this third equation, okay, when you substitute t is equal to 0, and certainly this become 3 times 2 g3 for the second order, for the third order of particular solution, okay. So this become the last piece of information, and then you go back once you know that this is A, B, C, D. You bring A, B, C, D, this A, B, C, D, bring it back and substitute it here over here. Right? This is the term A, term B, C, D, E. Okay, A, B, C, D, E. Right? Oh, sorry. Life turned out to be started getting more complicated. Okay, A, B, C, D, and this is a 3 times 2 becomes 6g3. And then you end up having this the fourth equation here, which is the coefficients start to be more complex to compute. Okay, so you end up now, you're moving the constant to the right hand side. This is g sub 3, missing the 3, 6g sub 3. Okay, so this one becomes the right hand side. This is the left hand side of c sub 1 to c sub 4. Okay, and if you want to reach the beauty of mathematics, you have to continue to find the general formula of c sub 1, c sub 2, c sub 3 by solving this symbolically. okay? That's even more complicated. You end up having C sub 1 in terms of all the other elements in the matrix and on the right hand side, and independent, and you want C sub 1, C sub 2, C sub 3, C sub 4 independent to each other, not just like in the equation like this. But I want to leave it for you to if anybody interested, you can continue to finish this problem by finding the general formula of C sub 1 sub 2 C sub 4. So this is just one case. Think about it. This is just one case. One case of what? One case of this type of force function. Okay, and this is just a case, the 8th case. Okay, here of x1 ct. Okay, and you know, it's a one case of complementary solution, and only the case of initial value condition. You can do it for boundary condition. Okay, how the formula gonna look like. Okay, you can do it one by one, case 1, case 2, case 3, case 4, case 9. Okay, and all of them gonna end up with system of equation here, but just a different coefficients here and different the right hand side here. And you need to solve the 4x4 linear equation symbolically to get the formula for C sub 1 up to C sub 4. And also, all of this is only for x sub 1. Only for x sub 1. You can see that how many combinations you need to solve to complete all possible solutions for x sub 1. And then you go to x sub 2. The x sub 2, luckily you don't need to derive any, you end up having 9 cases of this again. Okay, similar form, but the difference is that with the difference of x2 pt because of the right hand side, the difference of the right hand side of the equation down here, okay, you're gonna end up having a different system of resulting equation over here to find the constant. Let me tell you again, this one is not finished yet. Okay, just this case is that you need to go on and resolve this, solve C sub 1, C sub 2, C sub 3, C sub 4 as an independent formula. Okay, by solving the 4x4 equation symbolically. Wow. Okay, much more work. Okay, from the 3rd order, think about it, now to the 4th order. Don't even think about 5th order. But I want you to think about it because I leave you with 2 homework, which is the 5th order system and 6th order. The 5th order is over here. This first problem, the alternate current circuit. Okay, you have 2 inductance. You have no capacitor. You have 5 inductance. Okay, L sub 1, L sub 2, L sub 3, L sub 1, L sub 1. Therefore, the resulting equation to find I sub, and you have 3 response. You have I sub 1 t as a function of t, I sub 2 as a function of t, and I sub 3 as a function of 3 of times, okay, t. But I want to make your life a little bit simple that, okay, suppose I give you an input voltage function source in very easy form, only A sine omega t plus B times cos omega t. A very simple form, okay, because the system is already a difficult one. Okay, the second problem keep expanding, but I just take out the damper. We just keep only the spring here. But now you have 3 response of x sub 1, x sub 2, x sub 3. And I make your life easier that f if t is just a constant force. F is constant. It's not a time varying. Okay, there's no polynomial, no sinusoidal, just a constant force. Okay, I want you to derive the general formula for x sub 1, x sub 2, x sub 3. These are all. I think that if you're trying to do all possible cases that we already tell you about in this clip, you end up, you don't have to study anything more. You keep doing it for one whole semester. I think some of you might probably haven't finished it. Okay, so this will be the last example, and also no, this example is the last example, but not finished. all the combination that I've been talking about. And with the higher order, fifth order and sixth order, you might end up cannot be able to do it all. Just think about how many possible cases for the fifth order or sixth order, especially the sixth order. Okay, so this is just an exercise for you to practice your main knowledge and application from the last semester procedure about how to deal with ordinary differential equation. Okay, so that wraps it up, the first part, okay, of reviewing the ordinary differential equation. Okay, next time we're gonna go to a little bit more new idea, new detail for you. We call partial differential equation. In abbreviation, we call PDE. Okay, looking forward to see you in the next script.